that running? Excellent. So, yeah, for a bit of context, this is the first paper in a series that I suggested about distillation, but it's also a nice hook into another series that I will do at some point. So maybe we'll either revisit some points about this paper when I find the time and the energy to do a series on ensemble theory, which is actually the whole topic of my PhD. So some of you may be familiar with this paper. This paper actually has, I call it a brother or a sister paper, both in style and author, which you're probably more familiar with, which is the paper on dropouts. So I know it's paper club, but one of the things that I wanted to do today is actually talk about some of the things that have been done in this paper and some of the things that haven't been said in this paper, which are going to be useful about distillation. The reason being, it's typical Hinton style, and I know we are at Google, but it's also typical Google style, where there's a lot of missing detail and a lot of ideas that's thrown out there without expanding them properly. Now, that can be good and can be bad. In this case, it's good because a lot of the ideas that come from this paper, so this is an example of where it can be good. Okay? A lot of the ideas that are sort of half hinted at in this paper then ended up being in other papers, a couple of which I wrote, sorry. And I'm going to try and not plug my own papers at Paper. But the point being, this is an example of how you can still make a short paper with good ideas without spending too long writing it, that then leads to a pretty long line of research. So the idea of distillation, despite what Hinton might make you want to think, is not new. So if you look in signal theory, there are things called surrogate models. So the idea of transferring one type of modeling, the results of one type of modeling to another type of modeling, have been around since the 70s. That's still good. The paper is still very relevant, but I also try to put some context. So it's not exactly new. It's inspired from things that we also see in nature. The opening statement of this paper is one that is a little bit memorable. So hands up if you actually started reading the paper. How many of you knew what was being talked about in the first sentence? Okay. Right. Opening a machine learning paper talking about larvae is a pretty fun thing to do. So I'd like this to be remembered forever as the paper about larvae, although it's only one sentence. But the point is this: we have something that's difficult, big, and we create what is called a cumbersome model. So this can be one of many things. The examples that are given in the paper are an ensemble or a very large network with dropout. This is a paper from 2015, so it doesn't talk about recurrence or any of the other things. So what was complex in 2015 is probably actually pretty simple right now. But the principle still applies. The principle is we take something big that has learned from a data set, and then we take that and reduce it. And the reduction actually doesn't lose generality because there is a lot of waste in the big model. So if you want to boil it down into how are things represented, then this doesn't work. Earlier. So if we take, call it the input space and the output space, you have a function f which you can't observe, which is the reality, right? This is whatever rules govern this relationship. Then you have an approximate function, g, which is what you learn from a subsample of x and a subsample of y. And then you create a function, g prime, which is significantly less complex in order, which maps the same sets in the same way. That's basically the principle. It's explained in various different ways, but if we think about what this means relating to the examples given here, which are they're somewhere in the introduction, which are a large ensemble and a large network with heavy regularization. Those are two situations where we know G is very wasteful, right? So part of the trick is, which is not talked about in this paper, is knowledge that G is a wasteful function. It is something that learns well, but it uses way more resources than it needs. By resources, you can think of like number of weights, number of relationships, whatever the model be. I'm trying to talk in generic terms because I think the principle of distillation is more important than the examples in the paper. And that's the interesting thing. The interesting thing is that by the process of distillation, you effectively get rid of all of those extra computations that are required. Why is this useful? Why is it important? Computation, memory footprint, things like being able to put a model in a phone, those are still relevant issues today. Because models just become larger, phones become larger as well, but the difference between having Google infrastructure and having to run something on a phone is very different. And so that's the idea. The idea is to take the output of G and make G prime learn from the output of G. So this function is no longer learning from F, but it's learning from S, right? So you have a two-step learning process. And the somewhat interesting thing is that they go then deeper into how do you do this, and they use the softmax outputs. So normally when we do classification, and all these examples are talking about classification right now, but when we do classification, we have a softmax, and then we apply an argmax to determine what is the most probable class that we use as our actual output, which is a very good process. But in the distillation, the argmax is removed from the cumbersome model, so that the training set for the distilled model is the inputs, that those stay the same, and the softmax outputs of the cumbersome model. The reasoning behind that is that there is information in knowing how the remaining probability is distributed. Whilst obviously we know that the ground truth is hard, right? So if we talk, there's a little bit of a